Well, we're back with chapter 3 of the book, and we're going to be looking at 3 theorems today, and we may not get through all of them today, but we're going to look at the 3 theorems, and we're going to look first in chapter 3 here, and then we're going to maybe reference a little bit up into the end of the other book, the DC circuit analysis book. But let's go to chapter 3 and let's look at the 3 theorems. So there are 3 theorems in this chapter, and they're useful as tools to simplify an electrical circuit instead of doing the brute force method that we did to find all the currents and all the voltages. They make sense when we're discussing linear circuits. So linear circuits are basically circuits with resistors, capacitors, and inductors, but right now we're just going to look at resistors. They're applicable in a number of different situations and give us some valuable tools for getting specific answers when that is all we need. We use them in linear circuits today, but we must remember that they can be helpful in complicated nonlinear circuits so that they are useful beyond just what we do in this course. And these three theorems are the voltage divider, the Thevenin, and then maximum Thevenin and Norton, and then maximum power. So we're going to look at the voltage divider rule first. Voltage divider is a very simple way of finding the voltage across the AB terminals when we have a circuit such as the one we have right here. It's a one-step process, and if we look at it, we can say, okay, the current goes around this loop by itself, and there's no place for it to escape, so that it's a common I through all of them. So the voltage here at V2 is equal to what? Its relationship to the voltage V is R2 over R1 plus R2. So basically this ratio is the voltage across the output here from the A to B terminals is the ratio of that resistance to the resistors, the sum of the resistors, and that's the ratio. And basically we can say V2 is equal to V times R2 over R1 plus R2. So the bigger that the R2, the bigger the resistance. Now if you have more than one resistor up here, more than one, like 3 or 4 or 5, you can call all of the resistors RT. So again, we can say R2 over R1 plus R2, or you can say R2 over the total resistance. And this is the way we typically use it. V2 is equal to R2 over R total times the voltage in. If you just have 2, it's this, R2 over R1 plus R2 times V. So when we practice with this, we say, okay, now if I have a voltage in, and I have an R2, and then I have an R1 that's not in the output, and let's just give it some numbers. If I have R2 is 7,000, and R1 plus R2 is 10,000, if I have an input voltage of 10 volts, my output voltage is 7 volts. Now that's implying what? That we don't have anything attached over here to the across this resistance right here. And that usually, it can be the case, or it can be, we can say this is a very high resistance with respect to this, then it works. But basically, that's with this open. Okay, so we have a bunch of situations here. We have in the case of 3.1b, we have 7K and 3K, and 3.1c, we have what? We have 2K and 8K. What's the voltage across the output? Well, it's 2 over 2 plus 8 times 15, or 3. Here we have another device. This is called a potentiometer, or a pot, for short. You can crank this resistor up or down, and usually we say let's put it in the middle, but you can put it all the way to the top or all the way to the bottom, or you can put it anywhere in between, and you can see that as you move it, the voltage with respect to the output is it varies with respect to the input. So we could have like 10 volts over here, and we could have anywhere from 0 to 10 volts over here, depending on where we crank this potentiometer. So this R total here, is this the sum of the two resistors R, or is just this one resistor? It's really just this one resistor, isn't it? But it goes all the way across, the R total. So a potentiometer splits a resistance into two resistors. There are three terminals. When it is turned on, when the potentiometer is turned, the resistance between the two terminals increases while the other resistance decreases. It may be turned all the way to 0 or all the way to the full resistance. Okay. So the minimum resistance across a potentiometer is the 0 value, and the max is the value of the input in this situation. So the maximum would be, if we had an input of 2 volts, the output would be 2 volts. If we have it right in the middle, it's half of that, or 1 volt. Now a second kind of a switch is what we call a switch that picks various resistances, and it puts a ratio to those. So at various points in the switch, a different voltage is calculated. So here we have a variable switch. So if you put it to point E, voltage across V2 is 0 volts. If you put it across D, it's 1K over all this, which is the maximum. It's the 900 plus the 90 plus the 9 plus 1. So it's 10 millivolts. If it's across at C, it's 10K over 1 megohm, which is 0.1 volt. And as you can see, as you go through the switch positions, 10 millivolts, 100 millivolts, 1 volt, and then finally, what? 10 volts, right? Okay. So that gives you the idea of voltage divider. Now we use voltage divider a lot. We use it in this next rule, which is the Thevenin circuit. So we're going to use voltage divider in this next one, which is Thevenin. And if you want to know what's one of the most popular things we do in this course, it's this Thevenin circuit. So you cannot just say, oh, I'm not going to learn this, but this is something that you should know, that it's a very powerful tool, and we use it a lot. So you should basically make sure you understand how this one goes. Okay, so in most cases we can rarely see all the voltages and all the currents. Most of the time we really want to see something like this, and that's basically this is what we call a Lego approach to circuits, but many times that's what's necessary. This is called the input resistance, and this is called the open circuit voltage. Okay, this is called the Thevenin resistance, or the input resistance, and the Thevenin voltage. Now, what does a truck have to do with our course? Well, this may be something that you might be interested in, but this was something that was built at up in Detroit for the auto show a couple years ago, and it was 334,544 pieces of Legos, and it took 18 builders 2,000 plus hours to build, and it's a Chevy Silverado 1500. So it looks like a truck, only it's built totally out of Legos. So if you want to know what somebody did for a lot of hours, you can ask, well, you can't beat this. So this is something that took a lot of time and a lot of energy, but it was very impressive. And again, you can do about anything out of Legos, I guess, but that's what they did. Now, how do we want to build a Lego circuit? We want to come back to this, what I call the world's simplest circuit, or this circuit right here. So that's the Lego circuit that we want to come back to. But how do you do that? Well, what you do is you take a pair of scissors, and in this circuit right here, this is kind of one of those circuits like we call the accordion circuit, or the ones that were a little bit more difficult. But instead of asking for all the voltages and all the currents, I just want to know the voltage and current over here at this resistor right here. That's all I want to do. I don't want all these other ones. I just want this one over here on the far right. Okay, So in order to do that, I would have to go through the accordion principles, or I can do this thing called Thevenin, which is a little bit easier. I think in most cases it's a little bit easier. So what you do is you cut the circuit right here at the AB terminals. You separate out that 2K resistor from the rest of the circuit. Now what we are asking for now is to take the rest of the circuit and use these Thevenin rules and crunch it down to something that looks like right here, this same circuit right there. So we're going to find a new resistor, a new voltage, and a new resistor that would give us the same equivalent circuit as all this stuff over here. In order to do that, we need voltage divider, because we need to know the voltage across the AB terminals. Well, the only way to do that is to find the voltage using the voltage divider rule, which is what? Okay, it's 3 over 3 plus 6, or 9, so it's a third of 12. And you bring that voltage right down here. You don't mess around saying, well, what would, it's a 12. No, it's not. It becomes a 4. And the other thing you do is you take and you rub out, or you short out that 12 volt supply, and you say, starting at the A terminal, now not starting over here at the power supply, but starting at the A terminal, I walk this circuit back, and I come to this point here. Instead of this being in series like it was here, it's in parallel, because the 3 and the 6 are in parallel. See, this is rubbed out. This is what we do for our Thevenin. The 3 and the 6 are in parallel. So what is that now? That's a 2. That's 2K. So now we have 4 volts and we have 2K. Now the last thing we do is we reattach the 2K. But this is a lot simpler circuit to find the voltage and the current through that 2K resistor than the one we just had. This is a lot simpler circuit. So that's the basic rules. You cut the circuit, then reattach it. So you use glue to put the circuit back together. Okay, so you have these two entities. One is called the Thevenin voltage, and one is called the Thevenin resistance. And you have to find both of them. So the Thevenin voltage is the voltage across a pair of terminals with the circuit open at those terminals. Picture the circuit above with a pair of scissors. Cut the circuit at the AB terminals, then measure the voltage across the AB terminals with the circuit now open and the 2K resistor not a part of the new circuit. We remember the 2K but not part of the circuit we're creating, called the Thevenin circuit. The voltage between the AB terminals is the new V Thevenin. The voltage is the first component of the world's simplest circuit, or Lego circuit. So to find V Thevenin, you use voltage divider. Thevenin resistance is the resistance between the same terminals where the cuts in the circuit occurred, but in order to do that, you short out any voltage supply, and any current source you open. We'll say, I don't know what a current source looks like. Well, don't worry about it. You will later. But again, voltage source has to be shorted. They rubbed them out, basically eliminated them. And the current source is opened, or made an open circuit. All right, so that gives you a little bit of an idea how to find our Thevenin. But you start at the one terminal, you go to the left until you're into resistors, and you decide whether they're in parallel or series, and usually they're in parallel, and you basically, at that point in time, use the parallel rule, the product over sum rule, and find your resistance. Okay. So that gives you a little bit of a idea how to do this. It's not hard, it's just different, okay? It's a little bit different than what we've done before. So here we have a circuit. I want to know the Thevenin equivalent of this circuit right here. Okay, we've already done the cut. We've already cut out that whatever that thing was over there. So I want to know the world's simplest circuit, starting with this circuit right here. Well, first thing we do is we use voltage divider. 5 over 5 plus 5 is 0.5 times 18, or 9. So we take the 18 volts and we convert it to 9 volts over here, and this is known as V Thevenin. Our Thevenin, we start at the A terminal, and then you come back. You short out the 18 volts, and you come back to this point. You say, these must be in parallel. So you take the 5 and the 5, use the product over sum rule, and you get the 2.5K. So this circuit right here is equivalent to this circuit right here. Okay. Let's use the voltage divider for two resistors. Okay. Now this next circuit is a little different than the last circuit. I call this the case of the dangling resistor. So this resistor out here just left a dangle, right? It was part of a circuit over here, but now you've taken that circuit away, and this one just left a dangle. It's not used for VThevenin, but it is used for RThevenin. So let's just look at the rules. If you were to ask what's the voltage across the AB terminals, well, you'd have to ask what's the voltage drop across this and what's the voltage drop across this. But you look at this and you say, there's no current that can go through here because it can't go anywhere. So if there's no current that can go through it, what would be the voltage across this resistor? It's 0, isn't it? So if you know the voltage drop across here, in other words, if you knew the voltage drop across this with respect to this, you could find the voltage drop across here to here. And that's what we do. All right, so we look at this and we say 3 over 3 plus 6 times 15 is our VThevenin. So we can ignore this resistor up here when we're working with voltage. However, when we start our walk through the circuit with the voltage supply shorted out, we start at A, we come back through, and here we hit the 2K resistor, and we must include it in RThevenin. So we include it in RThevenin, we do not include it in VThevenin. That's confusing, I know, but that's exactly, those are the rules, and you just kind of set up, okay, I'm going to follow the rules. In this case, you start at A, you go through the 2K, and then you add the parallel combination of the 6 and the 3. So that gives you 2K plus 2K is equal to 4K. So our final answer here is 5 volts and 4K. And this circuit, believe it or not, is equal to this circuit. So this circuit right here has the equivalency of this circuit. If you attach any value of resistance out here, I don't care what you attach, this circuit and this circuit will give you the same answer of voltage and current through that resistor. Okay, that's what we're saying. Alright, so now we have some more sophisticated circuits. Now we just keep adding to them, but basically you got the idea. You just look voltage divider for the first for the VThevenin, and for RThevenin you take the voltage supplies and you short them out. In other words, go around them. Okay, so here's another one. In this case we have a 3 and a 6, which is a 2, and we have a 1 and then a 2. We can use that for voltage divider. So what is VThevenin? Well, it's 1 over 1 plus 2, or 3, so it's a third of 24, or 8. So that's our voltage divider right there. Now, here we start at A, and we come down to this point, and then we can go through the 6, or the 3, or the 1. And how do we handle that? Well, basically we handle it just the same way we handle everything else. This is in parallel, this is in parallel, this is in parallel, and this is in parallel. So they're all 3 in parallel. So you don't have to worry about are they in series or in parallel. These 2 are in parallel with this one, and you can get your answer. It's 1 over 1 over rule, or this would be the 1 over rule that you could use probably. And it would be something less than 1K, and in fact it is. It's 667 ohms, and there's your 8 volts. So basically this is an equivalent circuit to that circuit right there. And why would we use this circuit right here? It sure is easier than this one, isn't it? This is a hard one. This is a very difficult circuit to get. But you can make it this easy as this one. Okay. So is there any rhyme or anything to how this works? Yes, there is theory behind this, but basically it's not that complicated, but it's not really worth our while to go through and look at all the reasons why Thevenin works. Just it does work, and there's enough problems here that you could actually go back and work some of them. And you always have to ask the question, should I do the crunch method, the accordion method, or should I use Thevenin? Well, if they ask just for the resistance or the voltage or the current of that last resistor out there, always think first of Thevenin. Try to solve the problem with Thevenin if you can. Okay, if they ask for all of it, then you got to go back and do them all. Can you check with one against the other? Yes, you can, and they'll come out the same way, the same answer. Okay, so we are here, and we are looking at what we call a black box. Okay, we don't know what's in it, but you can assume this. Okay, Now that's if it's a linear circuit. It doesn't have to be necessarily linear, but you can kind of assume that it's this. Okay. All right. So that's something that you can always just kind of assume that it's that way. So we haven't really talked about independent and dependent sources yet, but here's an example of a dependent and independent source. Okay, so this one is a independent source. So these are independent sources. This one is a dependent source because it depends on this up here. So as this gets bigger, so does this voltage right here. See that? So this one would be a dependent source. This would be independent. So you can Thevenize this one. You can't Thevenize this one. Okay. A little different there. You can Thevenize this circuit. Hard to do it with this one. All right. So you use Thevenin to find the voltage or the current at the output of a circuit. And this is an example. So we're given this circuit right here. All I want is the voltage and current across the 5K resistor. So how do I do that? Pick up my scissors, right? I pick it up and cut it right there. Then I do the dangling resistor. I find the R Thevenin to be 1K plus 3 in parallel with 6, or 2K. So I basically come down and add those two together. And so I have 1K plus 2K, which is 3K. And that's my 3K right there. And I go with my 12 volts and 3 over 3 plus 6 voltage divider, which gives me what? 4 volts. So basically, I took the 3K and the 4 volts, and I used them to find this I out here, this I across this 5K. So I didn't tell you to use Thevenin to find this I and V, but if I gave you a circuit like this and I only want the V or the I across the output resistor, what's the easiest way to do it? It's Thevenize. So basically, get your scissors out, cut it right there, and then find the circuit we just talked about, put it back together then at the end, and you're going to find your V and your I. Now if you want to play hard nose about it, you can go back and calculate it and see if it works. But they do. They always work. So you can check yourself if you want to that way. Okay. Here is a black box. Okay. Right here's the black box. So in this case, we do not know what's inside. But if I measured the voltage and the current across the output, I could find what the voltage and the current is, or what the value of the V Thevenin is, and I could find what the R Thevenin is. So you can find that with the black box. You can find what the R Thevenin and V Thevenin is. Okay. So in this case, you remove the RL, use a voltmeter, and find the voltage from A to B, and that's your V Thevenin. Then with all voltages jumpered, the resistance to A to B is measured at 10K, so that's your R Thevenin, so it would be this voltage right here. So in other words, I would have to go in here and jumper out my voltage supply, but if I did that, I could find out what my equivalent circuit is to this circuit right here. There's another way to do it as well, but basically that gives you the idea that you can find what the value of a black box is. This would be the value inside that black box. You can Thevenize more than once. Believe it or not, you can do that. So if I first cut it here and put it back together again, look what happens. Well, I take the 18 volts, don't I? And I look and say, okay, I've got 18 volts to start with. But if I cut it, it drops to 9. Here's my R Thevenin, first time around. Then they can be put back together again, the 2K and the 1K, giving me 3K. Now I can find the Thevenin equivalent circuit of that one right there. And that one is the same as the original circuit. And then I can put my resistor back on at the end, and then I can find the current around that loop, which is 6 volts divided by 10K, or 0.6 milliamps. So this is a very powerful technique to finding the voltage and current around really complicated, long circuits, and it's very easy to do. All right. Now, I mentioned a little bit ago about that I could find, using the black box, I could find the I as well. That would be what we call the I shorted load. That's the shorted load. If you take the output A to B and short it, you can find that current. That is your I shorted load. And this equation is what you would find. V Thevenin is equal to I shorted load times R Thevenin. That's basically V equals IR, because you don't have any other resistor, just the one, and that's R Thevenin, and that would be the only resistance you would have. So that gives you a basically standard equation. Now, I shorted load is also used in another area. We're going to call it the Norton equivalent circuit. We're going to talk about that later. But for right now, we're just going to call it I shorted load. So if I short the output A to B, that becomes I shorted load. And if I measure that current through that I shorted load, that gives me this relationship. V Thevenin is I shorted load times R Thevenin. But that would be a circuit with just one resistor, R Thevenin, and one voltage supply, V Thevenin. Okay? So if I shorted A to B and measured it, that would give me I shorted load. And if I measured the voltage open circuit, that would give me V Thevenin. That would give me an indirect way to finding R Thevenin. What's wrong with using the I shorted load method? If you short out a big circuit, you could have a big pop, and that's why they don't want you to do this very often. Unless you're guaranteed you're not going to spray metal all over the place, and most of the time you don't know when you do this. You're kind of hunting and pecking to see what you got. So I shorted load is about the last way you want to do to open up a circuit and see if it's what its I shorted load is. But it's done. People will do this, and it begs the question why sometimes, but it's been done. Okay. So here is a circuit, and I wanted to find I shorted load. Well, basically, if I short this out, what have I done? I've killed my 3K resistor, right? It's no longer there. So I basically, at this point in time, find I shorted load by doing what? Okay. If I find V Thevenin, I can do that. I shorted load by shorting that out, and then that gives me what? That gives me my R Thevenin, doesn't it? So you can calculate R Thevenin based on V Thevenin divided by I shorted load. Right there. Okay, so there's a lot of ways of calculating these, and another way is to do this. So you're going to play with that voltage across the output until you get it exactly half of what it would be if you had an open circuit. So basically you have an open circuit, measure the voltage, and then you start playing with the resistance until you get the resistance, or the voltage A to B, to be exactly half. And if that's the case, then what do you have? You have the resistance here is exactly equal to the resistance there, and that's another way of finding the R Thevenin. So if you have a hard time finding it with a black box, put a potentiometer, a resistor, and turn it up and down until your A-B terminals go to exactly half of what they would have been if they were open circuit at A to B, and that'll give you R Thevenin. There's some other circuits with the same thing, but again, you got to be careful, but not as careful as you did with that I shorted load. The I shorted load is dangerous. This is not as bad. Okay. There's no risk to high currents that can damage equipment. So you can have a flashlight that you can say, okay, what is the Thevenin equivalent of a flashlight? Well, you can measure it, and it's 1.5 volts, and then you short it, and you give a current. So what would be the value of R Thevenin? V Thevenin over I Thevenin, or I shorted load, right? So basically that would give you a measure of ohms, about 1.0 ohms. So that's just one way of finding Thevenin equivalent circuits for things like a battery. Did you realize that a battery had an R Thevenin? It does. It's implied, and that's the way you find it. Okay. So that's one way of doing it. I shorted a load, flashlight battery, open circuit, another way. Just a bunch of ways of finding these two. So we're moving on. This is the long circuit. So basically, I want to know what the voltage across the AB terminals. If I attach a 3K resistor, what would be the current across that resistor? All right. So let's just look at that for a second. Okay, so first of all, you say, well, this is an impossible circuit to do. No, it's not. If you take Thevenin, you can do it. Okay. So what you do is you cut it here, find the voltage, Thevenin, find the I current, and then you basically put it back together. What do? You glue it together with just one resistor and one voltage supply. So you take all this stuff out, and you basically come down to one fewer voltage supplies. And then you do it again, you cut it here. And then you do it again, cut it here. And when you do that the third time, you're all set. Then you can reattach and you can find your voltage across the output. You say, is that possible? Yes, it's very possible. So that gives you a way of finding some very hard circuits to bring them down to something you can use. Instead of having to say, I just can't do it, you can now say, I can do it. So the circuit above and the game below have what in common? What is that game? That's the Pac-Man game, isn't it? And it kind of crunches one step at a time. So we kind of refer to this as the Pac-Man possibility. You crunch, and you're done. You can find it. It spits out an answer. Maybe you've never played Pac-Man. If you haven't, well, it's a good game. So you can enjoy that if you want to. But that's how you can look at it. Okay, so we're going to stop here, and we'll pick back up later, and we'll talk more about this chapter. Take care and have a good day. Okay, we're back again in Chapter 3 on page 17. And we're looking at multiple source circuits. In other words, if you have a two-source circuit, this would be two sources. You'd have a 15 and have a 30. And you would have more than one source, okay? Now, the following method will give you the ability to solve this multiple source circuit, okay? And right here, we have a circuit. It's called superposition theorem. This is superposition. And what you can do is you can look at the circuit from the point of view of this circuit from the point of view of the first circuit for the first power supply, and then you can look at it from the point of view of the second power supply, and then you can add the results together, and that gives you the final answer. So here I want to know this current flowing down through this 3K. I have a 15 volt supply and I have a 30 volt supply. I want to know the I flowing through the 3K. You can find that if it's a linear circuit, which all resistors it is, by adding the circuit for the I1 and the I2, and that gives you the final answer. So that gives you a way of solving more complicated circuits with multiple supplies using a process called a superposition. Okay, so superposition is an easy way to break down a problem using a method that says just solve the simpler problem, solve it twice, and that's it. Okay, so this one is one where we have two sources, one at the left and one at the right, and of course this is going to give you current going this way, and this one's going to give you current going this way. In this case, it's the current is this one minus this one, and that will give you the final answer. So basically here we're going to find out this current minus this current is the final answer. Okay, And that gives you the final numbers right there. I1, 1 milliamp. I2 is 0.5 milliamp. The final answer is 0.5 milliamp going left to right. Okay. Here's another one. So I stack two supplies together, and of course these add up to 10. But if you didn't know that, and if there was some confusion, you could say, well, I could find the current through this 2K resistor by saying, okay, I solve it for the 6, and then I solve it for the 4, and they add the 2 together, and that gives you your final answer, which is exactly the same thing as saying combine the 2 into a 10, and then you're all set. Either way works. Okay, so you can also have superposition on with two possible sources, and you can basically say, okay, if I have a first one and then a second one, and then I can come up with a whatever, and then I can find the final answer. Okay. Okay, so if I have one with 5 milliamps, one with 3 milliamps, another one with 5, another one with 3 going the opposite direction, what is my final answer? Final answer is 10, right? Okay. I have 5 and 5 going down, 3 and 3 going up. So it says here the answer is 8, which I think I made a mistake someplace. But again, you get the idea. Here, we use all three. We use voltage divider, Thevenin, and superposition. So this is a classic problem that we can ask you on a test or something like that, but it tests all three principles. So you're going to be using superposition, Thevenin, and voltage divider, all three in this problem right here. So how do you solve it? Well, you break it down into two problems, don't you? You break it down, take the 9 volt out, you break it down, there's the 18 volts. Here's my 18 volts, here's the 3K, and here's the 6K. You find the voltage A to B with that one. Then you find with the 9 volts, see, I take the 9 volt, put it over here, put the 6K up here, put the 3K down here, short out the 18. Now I find my V2 with this voltage, okay? And it is 3 volts. So now I've got 18 times 2/3 or 12, and this is 3. It's going to add up to 15 volts, right? So there is my voltage from my first source. There's my voltage from my second source. Add them together and you get 15 volts. So that gives you the final answer right there. 15 volts. And here's my 2K. Here's my resistance. So I come to the 6K and the 3K. You jump out both supplies. That's giving me my 2K resistance. And that gives me my Thevenin equivalent circuit. Okay, that gives me my final answer. So now we're in for a treat because we're going to work some of these problems, and we're going to start answering some of this stuff. And let's go through some of these, okay? So we're going to find the page 23. We're going to look at some of these circuits, and we're going to start answering some of these questions. Okay. All right. So I have a calculator. We're going to start answering some of these questions, and we're going to work on some of these with the so let's go back. Okay. Okay, so we're going to look at the okay, so here we go. So problem number 3.1. From 324A, find V out when the wiper is at the top, middle, and bottom. Find the voltage out. So we have a circuit there. And 324A. So find the voltage when the wiper is at the top, middle, and bottom. So for 324A, we have a circuit with 15 volts. Oops. Okay, plus 15 minus. Come out here, we go through a 30K resistor. We come down at a point with a potentiometer. We come back. Now at certain points they want to know what the voltage is across the output. So here's my V out. And this is 20K. So I believe that at the top of this is right here. And that would be this would be the circuit. So it would be 15 volts, 30K up here, and then 20K right here. So what would be the voltage out of this circuit? What's the formula? Well, it's 20. Remember, it's the voltage across the output. It's 20 times 20 plus 30, the whole thing times 15. Okay, so it's 20 divided by 50 times 15, or 6 volts. Then they want to know at the bottom. At the bottom, it's 0 because it's down here at 0. So at the bottom, this would be at the top. At bottom, 0 volts. And in the middle, so that's the interesting one. In the middle, we are at 15 volts. Whoops. I'll do this again. $15 volts, 30K, and it splits it exactly half. Here's 10K, and here's 10K, and I want to know across the AB terminals. So VAB is equal to 10 over 10 plus 10 plus 30 times 15. So it is 10 over 10 times 15 over 50, or what? 10 divided by 50 times 15, or 3. Volts. So that gives you a little bit of an idea about how these work. So let's do another one. Okay, so that's number 1. Okay, number 2. So there's 4 positions of the switch. There's the it says at each of the 4 positions of the switch. So there is a 1, 2, 3, 4. We're going to find it at B, C, D, and E. So we're going to find it at B, C, D, and E. So this is problem number 2. And here we have 100 volts. So our output is 100. It's easy. Now here we have 7 meg. And then we have a terminal, and then we have 2 meg. We have another terminal. This is the B terminal, the C terminal, the 700K. That's the D terminal. The E terminal is 200 meg or 200K. We go to the E terminal, and we have 100K. And then we have the bottom, or the I'm sorry, I'm on the wrong one. I'm working on the C instead of the B. I'm sorry. So we're going to start over again. Sorry about that. We'll get there. All right. So this is number 2. In this one, we have 25 volts. And we have terminals at above the 900K, the 90K, the 10K, and the OK. Oh, I mean the 0 volts. So basically, we have, let's call this A, B, C, and D. Although they're not labeled there, we should label them, and then we can say, what is the V out at VA? What is VA with respect to the bottom down here, or 0 volts? VA is equal to what? 25, right? It's the whole resistance, so it's all of it. VB is equal to the output resistance, or 90 plus 10, or 100K, over the all of it, which is 900 plus 90 plus 10 times 25. So this is 100K over what? 900 plus 100 is 1000K, or 100K over 1000K, or 1 meg. Times 25. What does that be equal to? 2.5, right? What would it be at C? Well, that one is 10K over 1000K. Or what would that be times 25? Is 0.25 volts. What would be V at D in 0 volts? Now we can solve the problem at the next one. So let's now go and solve the one that's asked for. At C, find all the positions A through F. So now I was getting ahead of myself. Now we can solve this one. So number 3. So here we have 100 volts. Whoops. And we have a bunch of resistors, don't we? We have a position at A, and we have a resistance, 7 meg. We have a position at B. We have 2 meg. This is A. This is B. And we have another terminal here at C. And then we have 700K. Then we have a position at D. Then we have 200K. We have a position at E, and then we have another 100K, and a position at F. So the A and the F positions are easy. So what would be VA? That'd be 100 volts, right? All of the voltage goes across it. What would be the voltage at B? Well, it's the voltage across B to F over the sum of the whole thing. So what would be the sum of the whole thing? I mean, this is 10 meg, so the denominator is 10 meg. And what would be the, it would be, what would be the numerator? It's the resistance across here. It's 7, or it's 2 plus 1 is 3, so it's 3 meg over 10 meg times 100 volts. So it would be 3/10 of 100, or 30 volts. So VB is 30 volts. VC is what? And this one we have 1 meg over 10 meg times 100, or 10 volts. What's VD? It's 300K over 10 meg, which is equal to what? 0.3 volts. And then VE is 100K over 10 meg, or 0.1 volt. What is VF? Is 0 volts. Okay. Okay. I got these wrong. This one should be 3 volts. Sorry about that. This should be 3 volts. And this should be 1 volt. 0.3 divided by 10 times 100 is 3. And 0.1 divided by 10 times 100 is equal to 1. So these are the right numbers: 100, 30, 10, 3, and 1, and then 0. Okay, moving on. All right, so number 4. For the circuit in 325A, find V Thevenin and R Thevenin. So now we're going to go through and we're going to look at some of these circuits. We're going to say, what is V Thevenin and R Thevenin for this circuit right here? So 325A. Okay, so problem number 4 says find V Thevenin and R Thevenin for this circuit right here. So basically, what is problem number 4? Is 60 volts and 50K and 50K. Okay, 50K, 50K, and here's my AB terminals. So the rules say find V Thevenin by doing the voltage divider. So voltage divider, V Thevenin, is equal to 50K over 50 plus 50 times 60. So what would that be? That's 30, right? Half of 60 is 30, so V Thevenin is equal to 30 volts. What would be R Thevenin? Well, you start at the A terminal, and you say, okay, it's in parallel, so it's 50 in parallel with 50, or 25K. So my equivalent circuit in this case is equal to 30 volts and a 25K resistor. So that's my V Thevenin and my R Thevenin for that circuit. The next one. So let's go to the next one, which is B, 325B. Okay, so let's solve this one. Now this is a little different because we basically have a, this would be, okay, this is problem number 5, I think, right? Yeah, number 5, 3-5 is the problem for 325B. So problem number 5 is 20 volts and a 30K, then a 30K over here, and then a 25K up here, and then the A-B terminals. Okay, so first thing is V Thevenin. And if I look at that, what's the current through here? I is equal to 0. So there's no voltage difference between from here to here than there is from here to here. If the I is 0, then VAB is equal to voltage divider. So basically for voltage divider, it's the same circuit we've done before, is equal to 30 over 30 plus 30 times 20, or 10. But our R Thevenin does change, right? Because we have to go through the R Thevenin to get to the final answer. So it's 25K plus 30K parallel with 30K, or 15K. So the answer here is 40K. So the answer for R Thevenin is different. The answer for V Thevenin isn't. So our final answer here is 10 volts and 40K. All right, that's our final answer for that circuit. This is V Thevenin. This is R Thevenin. Number 6. So for number 6, we've got a circuit with 24 volts. And we've got two resistors up here, don't we? They're in parallel. We've got a 60 and a 60. That's easy. That's just 30, right? That's exactly what that is. So we can do that immediately, or we can just leave it alone for right now. And let's just leave it alone for right now. And the 50. Okay, this 50K right here. And these are 60s. Okay, so what is the VAB? Well, it's 50 over 50 plus 30 times 24. It's 15 volts. What is R Thevenin? We have 50 in parallel with a 30, if you want to. That's one we've done. Or we have a 50 in parallel with a 60 in parallel with a 60. Let's do it this way. That's equal to 18.75K. 50 times 30 divided by 80. Oops. Okay, so that gives us our answer for that circuit right there. So we can redraw it. So that whole complicated circuit is equal to this: 15 volts, 18.75K. So that's equal to that. Okay, so then for D, it's if it's in the middle. So basically for D, that's number 7. So the question number 7 says, if the circuit of D, find R Thevenin if the wiper is in the middle point of the 20K resistor. So basically we have a 20K resistor, but we have it split equally. So this is number 7. So we have a 10 volt, and we have a 20K. We have a 10K up here, and then we have a 10K down here. So that's our A and our B terminals, and a 10K right there. So basically, what do we have? We have a Thevenin equivalent of R Thevenin is equal to 5K, and V Thevenin is equal to 5 volts. So we basically have 5 volts and 5K. Alright, so that circuit is equal to that right there. So that gives you a little bit of an idea. Okay? Alright, so let's go on to number 8. Alright, so if you have a 75K ohm resistor attached to the circuit of 325A, so if I add a 75K resistor across that output, okay, so number 8 says if you start over again, we should have kept these answers, shouldn't we? So for number 8, Find the current through a 75K resistor across the terminals. What is the voltage across the resistor? So I want to know V and I across the 75K resistor in 325A. Okay, so I go down to 325A and I draw the circuit. If you remember what we had a 60 volt and a 50K and a 50K, right? So now I want to add to this. I want to add a 75K resistor. And I want to know the I through it, and I want to know the V across it. Okay, so let's just do this, not the crunch method, but let's just do it with Thevenin. So basically, our Thevenin is equal to what? Well, it's 30 volts, if you remember from before, and our R Thevenin is 25K. And now I can add the 75, and I can add, what's the current through it? Well, the current through it is what? It is V. I is equal to V over R, which is 100K. 75 plus 25 is 100K. So what would that be? 30 divided by 100. 0.3 milliamps, right? 0.3 milliamps. So now what would be voltage across the 75K? It's 0.3 times 75, or 22.5 volts. So I have my two answers. There's the voltage, there's a current, there's a voltage through it. Okay. Number 9. Now again, these are, if you attach, I want to know the voltage and the current, if you attach a 60K resistor. Okay. Across B. So I've got B here. So 3.9. I've got the circuit. I got the voltage, and 30K and 30K. And I got the dangling resistor. And then they ask if you put a 60K across it. So this would be the 60K resistor right here. So if it's open circuit, what would be the voltage across it? The open circuit, VAB, is equal to 10 volts if it's open circuit. We're going to ask the same question. If you put the resistor across it, what would it be? So we're going to ask that question in a minute. But if you remember, this would drop to 10 volts. 30 and 30 is 15, plus 20 is 40. This is the dangling resistor, remember that. So now we want to add 40 plus 60. And what would be the current through that? I is equal to what? 10 divided by 100K. It's 0.1 milliamp. Okay, now what will be the voltage? For 6 volts. VAB is equal to 6 volts. So, did it drop? Yes, it dropped. That's what we'd expect. So that would be our answer. It dropped from 10 to 6. All right, so you found the current, the voltage, and it dropped. Okay, number 10, 325C. So if you have a circuit, number 10, and you add 12.5K resistor. So let's add the 12.5K resistor to it. Okay, so this is number 10. So with this circuit right here, $60 and $60. $50K. And I add a resistor. What value resistor do we add? 12.5K. What is the voltage across the resistor? Okay, so what is the current and voltage across? 12.5K ohms. Okay. So let's go down and solve it. Okay, so here we go. We do the Thevenin. The Thevenin was 30. It was 5/8 or 15. So we have a supply voltage. Our V Thevenin is 15, and our R Thevenin was 30 times 50 divided by 80, or 18.75. 18.75K, right? Now this resistor down here is a 12.5K. So what would be our current? It's V divided by 18.75 plus 12.5. So this one's 30, the resistance, total resistance is V over R, which is 31.25K. So it's 15 divided by 31.25, or 0.48 milliamps. And what would be the voltage? 0.48 times 12.5 is 6. So my V across AB is 6 volts. Okay. Okay, so number 11. Number 11. Find the current through a 10K resistor connected across the AB terminals. So I've got a 10K resistor of figure 325D. Okay, 325D. So this is 325D. I've got the 10 volts. I've got the 10K, and I've got the 10K. And I've got the 10K over here, right? So this solved to 5 volts and 5K and then 10K, right? And that's voltage across that. Or let's go to the current. Current is equal to 5 divided by 15, or 0.33 milliamps. And then the voltage would be 3.33 volts. Now, if I rework this problem, I have to go back and redo it majorly, because they say, now what if I put the wiper at the top and at the bottom? Next, connect to the top of the wiper. What is the voltage across this? So if it's the top of the wiper, if it's at the top of the wiper, it is, this would be at middle. The top of the wiper, it's 10 volts, but you got 20K here, and this is 10K. What's my voltage here? My voltage here is VAB is 10 volts because they're in parallel, and my current would be 1 milliamp. At the bottom, this would be at the top. At the bottom, it would be this, wouldn't it? It would be 10. Whoops. Well, so figure out how to get rid of that. Okay, well, don't worry about it for right now. Okay, so we've got a value here of 10K, 10 volts, excuse me. Let's just start again. We have a value of 20. We have a value of 10. So for at the bottom, so it's at the bottom, so it's 10 volts, and I have my 20 right here, and I have this connected to my AB. So what's my VAB? 0 volts, right? What would be my current? (10 divided by 20 K, or 0.5 milliamps. So that would be my voltage, and that would be my current. So if I had it at the bottom, it would be 0 volts, but I would have a current through it. Okay, so that's number 11. No, excuse me, that's number 10. That is number 11. So let's stop here, and we'll pick back up with the next group. We'll start with number 12, and we'll finish this with the next batch. Take care and have a good day. Okay, so we're starting with problem number 12, 3-12, and it says find VTH and RTH for the figure 325E. So this would be problem number 3-12. And so we look at 325E, and we see a mess. So we have 4 volts, and we have 2K, we have a 1K, we have 2K, we have 1K, 2K, we have 1K, and we have another 2K, and it says find R Thevenin for this. So we have, here's our A and our B terminals. So we can cut it either here or here. I'm going to choose to cut it here. So now we're looking at the circuit to the left without the circuit to the right, and the voltage, VThevenin, is what? Use voltage divider. It's 2 over 2 plus 2 times 4, or it's half of 4, or it's 2 volts. And what is our Thevenin? We start here and we walk back. There's the 1K, 2K and 2K are parallel, so that is 2K. So now we have 2K, and we reattach. Notice how we reattach. We reattach, and we put in this 2K right here. We have a 1K. All right, so now let's look at it again. Well, it's the same as we did before, but now we cut it again. We cut it right here, and we say, what is voltage VThevenin? Well, it's 1 volt. And what is R Thevenin? It is 1K plus 1K, or 2K. We do this. $1K and 2K. So what are we doing again? We're going to cut it again. So now it is 0.5 volts and 2K up here, and you got the story right. You got the story. It's 2K, and we have 2K right here. So what do we have now? Well, we're going to have to Thevenize this, but this is easy. 0.25 volts and 1K up here, because now there is no extra 1K, so it basically is 1K. So there's our Thevenin equivalent of this whole thing. So if you Thevenize this whole thing, you end up with this thing right here. Now it says, now add a 1, now connect a, so the first thing is this is our VThevenin, this is our R Thevenin. Now add a 1K resistor, and they want to know the voltage and current between A and B. So the voltage would be 0.25 times 1 over 2, or 0.125 volts. What would be the current? Well, it would be 0.25 divided by 2K, or 0.125 milliamp. And those are our two answers, final answers. So our final answers are 0.125 volt and 0.125 milliamp. Okay, those are our answers. So now let's go to 313. Use the flashlight battery from the text and the data VThevenin and I shorted load to find R Thevenin of the battery. So VThevenin is equal to 1.5. I shorted load is equal to 2 amps. R Thevenin, well, it's V equals IR, so V 1.5 is equal to 2 times R Thevenin, or R Thevenin is equal to what? 1.5 divided by 2, or what? Equal 0.75 ohms. 314. Okay, so VThevenin is equal to 9. I shorted load is equal to 1.25. Find R Thevenin. So it's 9.0 equals 1.25 times R. R equals 9 divided by 1.25. or 7.2 ohms. Yes, sir. Okay, so number 15. Given the voltmeter of 326A has a very large okay, so it says given that the voltmeter has a resistance and the ammeter of 26 has a varying resistance and B has a very low resistance. Okay, so find R Thevenin of the black box if VAB is 100 millivolts and I shorted load is 0.1 ohm. Okay, so we look at it and say, okay, what are we looking for? Well, we're looking for R Thevenin equal what? It's R Thevenin equal V Thevenin over I shorted load. So if I have VAB or V Thevenin, it's equal to 100 millivolts, 0.1, and I shorted load is equal to 0.1 milliamp. So it's 0.1 over 0.1, or what? And this is 0.1 times 10 to the minus third, so it's 10 to the third, or 1 k ohm. Okay. .316. The 315 says, given that the voltmeter has very high resistance, it should say high resistance, and the ammeter has very low resistance. That's how that should read. That the word high is missing there. Number 16, given that the voltmeter of 326 has very high resistance, the ammeter has low resistance, find R Thevenin if the readings of VAB are 2 and I shorted load is 1 milliamp. So here again, R Thevenin is equal to 2 over 1 milliamp. Okay. What would be R Thevenin? So it's 2 divided by our 2 times 10 to the third, or 2k ohms. So now I have a circuit with 2 volts and 2k up here, and then they say add 3k. So now we want to find the current through this. So I is equal to 2 volts over 5k. What would that be? So it's 0.4 milliamps. Okay. 17. Okay, so D is a black box. V Thevenin is equal to 10. I shorted is equal to 2. So V Thevenin is equal to 10. I shorted load is equal to 2 milliamps. Now attach a variable resistor between A and B and turn until VAB is equal to 5. Okay, so if I were to look at this and say, at what point, I've got a circuit like this, right? And I've got a resistor up here, and I've got a resistor over here. And when it's open circuited, it would be 10, but when it drops to 5, this resistor has to equal this resistor. So if I find this resistor, I know that this resistor, if it's equal to that, would drop this output to half of it. So that's what they're asking for. So let's calculate R Thevenin. R Thevenin is equal to what? 10 divided by 2 milliamps. 10 divided by 2 is 5 times 10 to the third, or 5k ohms. So this is 5k ohms. So if you put 5k ohms here, it would drop the voltage, the 10 volts, to half. Now move the variable resistor until the load voltage is 7.5 volts. Calculate the new variable resistor. So at that point in time, we don't know what this is, but let's just say, okay, we know what this is 10, this is 5k, and we've got a voltage out of here of 7.5 volts. We don't know what R is. R is unknown. But I have 7.5 volts. So voltage divider 7.5 is equal to R over R plus 5k times 10. Solve for R. Alright, so let's do that. Everybody see how you can use voltage divider and use an unknown resistance? That's exactly what you do here. So let's do that. So it's R times 7.5 plus 7.5 times 5k is equal to 10R. So with 5R plus, okay, so now we've got 2.5R is equal to 7.5 times 5, 37.5. So 37.5 K is equal to 2.5 R. So 37.5 divided by 2.5 is equal to 15. So R is equal to 15K. You can check that out and see if that works, but that is what it is. So this is our R is 15K. So that's 317. Moving along, we skipped through 18 and 19. We didn't have an 18 and a 19, but we're going to 20. 3-20. Vthevenin of a black box is 4 volts. Adding a resistor between the AB of the 8K drops VAB to 2 volts. Find I shorted load. Okay, so we have a Vthevenin of 4. Adding resistor of 8K drops it to 2 volts. So basically, we know that adding a resistor out here of 8K drops it to half, so this has to be 8K up here. Find I shorted load. So this gives me 8K, but now it's going to ask you to go back and find I shorted load, which is 8K and 4 volts. What would be the voltage, or what would be the current if you shorted this? Well, it is 4 volts divided by 8K, or 0.5 milliamps, equal to I shorted load. Next, remove the 8K and calculate the current through a 32K resistor attached between A and B. So then we go back and we say, okay, I've got 4 volts, I've got 8K, and I've got 32K. Well, what would be my current through here? Well, it's 4 volts divided by 40K, or 0.1 milliamp. That's 20. Okay, number 21. In figure 327A, find the voltage of the 2K resistor of the 6K resistor between A and B terminals. So basically, in this figure of 327A, find the voltage of the 2K resistor of the 6K resistor. Okay, so now, in this case, we have 48 volts. And I'm going to draw this differently. I like drawing it with a square goalpost instead of not. So basically, I'm going to draw it like this. We can do this if we want to. So this is 1K, this is 2K, this is 3K, and this is 6K. So I can go around this loop and do voltage dividers. So they want to know the voltage across the 2K, or they want to know voltage across here. So basically I can do voltage divider around this one, I can do voltage divider around this one, and these two will never interact with each other. So basically it's 2 over 2 plus 1, or 3 times 48, and that's the voltage at A. This is my A terminal. So VA is equal to 2 over 2 plus 1 is 3. So it's 2 divided by 3 times 48, or 32. So the answer here is 32. And the voltage of the 6K is what? V at B is 6 over 6 plus 3 times 48, also equals, it's 2/3, so that is also equals 32 volts. Okay, what's the voltage between A and B? Well, it's 32 minus 32, or 0 volts. So the VAB is that. So now let's go to B. .322. In figure 327B, find the resistance across the 1K terminal, across the 1K resistor. Next, let R equal 8. Find the voltage of this resistor. Find the value that reduces the AB to 0. Okay, so first of all, let's draw the circuit. 24 volts. And then 2K. And 1K. Okay, come over here. And I have 4K and an unknown R. So here I have 1 over 1 plus 2 times 24, or 8 volts. So the voltage here is at VA is 8. Okay, next, R equals 8. That would be V at B is equal to 8 over 8 plus 4 times 24, or 2/3 of 24, or 16. Okay, find the voltage of this resistor. Okay, next, okay, find the voltage of this resistor. That would be 16. Find the value of R that reduces AB to 0. So it would be, okay, so this would be 8 volts. So I could say VB equal 8 equal what? R over R plus 4 times 24. So that has to equal, that's an unknown. So basically I have to say 8 times R plus 4 is equal to R times 24. R times 24, okay? 8 times R plus 4, or 8R plus 32 is equal to 24R. So I have 16R on the right, I have 32 on the left, R is equal to 2K. So if I had R equal to 2K up here, I would have a VAB of 0. So that's a story problem. Okay, so now we're going to be asking to do the same thing with these other ones. So now we're going to ask this question of 323. Find the current in that resistor. So basically what I'm going to do now is I'm going to say, okay, so here we've got a voltage, and I'm going to do this, and I'm going to cut that resistor out. And I can do that, can't I? I've got 12 volts, and I've got 2K, and I've got 4K, and I've got, I'm going to cut that resistor out, and I've got over here 6K, over here I've got 3K. Alright, So what's VA? Is equal to 4 over 4 plus 2 times 12, or 8. What's VB? 3 over 3 plus 6 times 12, or 4. So VAB is equal to 4. Okay. Now, what is R Thevenin? That's the hard one. Well, if you draw it like this, it's not so bad. You start at A, and then you walk down, and you've got a 2K and a 4K. And then you go through the voltage supply, and then you come to the other side, and you have a 6K or 3K and a 6K. So what is the resistance here? What is the 2 times 4? That's 8 divided by 6, or 1.33K. So this is equal to 1.33K. What is the resistance here? It is 3 and 6. That's 18 over 9, or 2K. And you add these two together, so it's 3.33K. So now I come up here and rebuild my circuit. I've got 4 volts, and I've got R Thevenin of 3.33K. And then I attach my 6K. Now I ask, what's the current through it? Well, it better be 4 divided by 9.33K. That's my I. Okay, what is that? 0.428, right? Milliamps. So everybody see this drawing down here. It's kind of a scribbly drawing, but it does show you the 2 and the 4K are in parallel, and then you come around, and this shorts out, so that becomes all one big short. Then I come back to my 3K in parallel with my 6K, and that goes to B. Okay. Number 24. Okay. Find the current in that circuit right there. So basically we're going to find the current across that. I assume there's very low resistance. Okay. 6. So I've got 10 and 30. I've got 30 and 10. So my VA is 30 over 40 times 6, or what? $4.5, and V at B is 1/4 of 6, so it's 10 over 40 times 6, or 1.5. The difference is 3.0 volts. Now, what is my R Thevenin? So this is my V Thevenin, or VAB is that. My R Thevenin is equal to 10 in parallel with the 30K plus another 10 in parallel with the 30K. Does everybody see that? So 10 times 30 equals, divided by 40 equals 7.5. So again, this is 7.5K plus 7.5K, or 15K. Now they ask for what's the current across here, which is your I shorted load. So basically you redraw the circuit. What? 3 volts and 15K up here. What's I shorted load? 3 divided by 15, right? Or 0.2. milliamps. Okay, this is 324. Okay, 325. For figure 327A, the 1K has a tolerance rating of plus or minus 1%. Assume that all our resistances are their nominal value. Find the maximum voltage between the terminals of A and B. So here, I go back to 327A. So this is 325. I go back to this voltage, and I say 48. And I look here, and I've got 1K. And I've got 2K down here. And I've got over here, I've got 6K. And I've got 3K. So I want to make this the maximum. So make it as big as possible. This has to be bigger than that. So I drop this as much as I possibly can. So basically I say 2K over 2K plus, make it the smallest numbers I possibly can, which would be what? 1K times 0.99. Or 990 ohms times 480 or 48. So that gives me my value, 2000 divided by 2990 equals times 48, and that gives me 32.107 volts. And the 6/9 gives me my what? That gives me my 16. So my maximum voltage is AB is 16.107. That's my maximum voltage. Okay, number 26. It says for 327B, assign an internal resistance of 50 ohms for the ammeter. Then calculate the current through the ammeter. So basically we're going to go back to that circuit, and we found I shorted load, but now we're going to add a little bit of resistance, right? We're going to go back and add a little bit of resistance. So let's go back, and on 326 we go back to 327D, and we have the 6 volts, and I have 10K, and 30K, and I have the ammeter, and I have 30K, I have 10K. So this resistance here was, okay, it was the voltage that the VAB was 3 volts. It was 4.5 minus 1.5, and my R Thevenin was 15K. It was 30 in parallel with 10 plus 30 in parallel with 10, or 7.5 plus 7.5, or that. Now we go back into this circuit. We have the VAB of 3.0, 3 volts, and we have a 15K up here, and we add 50 ohms. So what would be our current? Okay, so we add a little bit of resistance, and we say, is that much? So it's not. It's 3.0 divided by 15,050, and that's equal to what? 1.99 1.993 milliamps. Okay, so now for 327 dB, we have find the current between A and B for the following values, the resistance between A and B. So here we're going to go back, and in 327, okay, we're going to go back to 321B, and we've got 24 volts, and we've got 2K and 1K, 4K and 1K. Okay, so now we're going to find the current between A and B for the following values. Okay, so well, if they in 327B, they'd have to give you the value of R. So I don't know how to do that problem other than if you put the value here, but I'm going to have to go back and work on that problem. So again, let's ignore 327 for right now. Okay, so let's go to 328. Okay, so 328. For figure 328A, find I. So in 328A, so in figure 328, we have two values of voltage. I have a 10 and a 20, and I have a 5K resistor. Okay, so I can just say, okay, I can do it with 10 and the 20, add them together, that's 30 volts and 5K, so I can say 30 volts divided by 5K, or 6 milliamps, and that's, I can solve that way. Or I can solve it by solving it with 2. I can solve it with the 10, and that would give me 10 volts and 5K, or that's 2 milliamps. And then I can solve it with the 20 and the 5K, and that's 20 over 5K, and that gives me 4 milliamps. And either way, they add up to this value up here. So that's all you need. Okay, 329. For figure 328B, find I. So this one's a little more stressful because you really don't know, but you do know. This is 20 going in one direction, and you got 10 going in the other direction. So you got 5K, and I've got 10 volts going in the other direction. So basically, I can do it with that. I can do it with 10 volts. The 20 and the 10 would be like 10 pushing in that direction. So the answer really is 10 volts divided by 5K, or 2 milliamps. But I can also solve it by doing this: 20, 5K, and that would give me what? That would give me 4 milliamps pushing in the right direction, and then I can solve it with the left direction, and it's 2 pushing in that direction. So 4 minus 2 is 2 milliamps, which is the same as up here. Okay, so that gives me 29, 30, 30 is, here is a little bit more, 328C, so 3-30, and this one I have 72 volts, and I have 12K, and I have 6K, and I have 12K, and I have, over here, I have 24 volts. So I can solve this. The best way to solve this is with superposition, and I do it by the following. Do the one circuit with the 12K. Now this 12K you jumper out, so basically now you have a 12K, and then you have a 6K over here, which we're going to just do this to. We're going to find the Thevenin of this, and then we're going to add the 6K over here. Okay, so we're going to do that with Thevenin. So we're going to find the Thevenin of this, which would be 12 and 12, which would be 36 volts. And our Thevenin of 6K, and now I add the 6K back in, which would be 12 volts. So 36 divided by 12 is what? 3 milliamps. So basically I have 3 milliamps based on this, on the 72K. Okay, so based on the 72 volts I have 3 milliamps. Now what do I have with the 24 volts? So I'm going to redraw 24 volts and 12K up on top, and this other 12K, bring it down here. This is this 12K. Now I put this 6K out here, and I have 12 and 12 gives me 24 divided by 12 and gives me 12 volts, half and half. Now I have my 6K up here, and I add my 6K, and I have 12 volts, 12 K ohms. I have, for my 24 volts, I have 1 milliamp. So you add the two together, and I have 4 milliamps. So basically, to solve this problem, I do it with, and I get the 4 milliamp as my answer. Okay, number 31. So now I'm going to go to D. So for this one, I go to 328D. So I have 25 and 5, and I have 15 pushing in the other direction. So I can do this by saying 25 and 5 is 30, minus 15 is 15. 15 volts divided by 10K is equal to, in this direction, 1.5 milliamps. Or I can say, solve it for the 25 for the 25 volts, 10K, I get 2.5 milliamps. For the 5 over 10K, I have 0.5 milliamps. And for the 15, it pushes in the other direction, I have minus 1.5. So you add these up and you come up with the same thing, 1.5 milliamps. Okay. E and F. Okay. So 332. E is 40 volts and 30K. And then I have over here, I have 10K and I have 20 volts. So find the Thevenin equivalent of that. So basically at that point in time you say, well, I'm going to short out this supply, and my V Thevenin is equal to 10 over 10 plus 30 times 40, or 10. If I do it the other way, I can draw, I'll redraw. 40 volts, 30K, 10K. That's one way. The other way is 20 volts, 10K, 30K. And then I can find V Thevenin here. It's 10 V Thevenin the other way is what? 30 over 30 plus 10 times 20, or what? 15. Add the two together, I get 25. So V Thevenin total is 25. Okay. What is R Thevenin? Well, it's 10 in parallel with 30, or 7.5. Okay. So I can redraw this. It is 25 and 7.5K. I'm just going to sneak down and I'm going to solve 34 as well. So if this circuit, I can add a 10K resistor and find the voltage across the 10K resistor. So what would be the voltage across the 10K resistor? It would be 10 over 10 plus 7.5 times 25. Or 14.28. 14.28 volts. That's equal to VAB. For number 334. Okay, so we come back up here, and now we solve the same thing for the last circuit, which is 333. And I have my voltage, my first voltage, and I have my resistor, and I have my second resistor, and I have 20 volts going in the other direction. Okay, so now what do I have? Well, I have 30, or excuse me, I have, with this one gone, I have 10 volts, but with the 20 volts, I'm going to redraw the 20 volts, 20 and the 10 up here, and I have the 30 over here, so I have 3/4 of 20. 3/4 of 20 is 15, but it's in the negative direction, so I have minus 15. So I have a VAB of minus 5. So I can redraw. I can say like this, 5 volts, that's a minus 5 volts because it's pointing down, and I have my 10 and 30 or 7.5K, and there's my Thevenin equivalent circuit. Now if I add a 12.5K resistor across this, what is my VAB? It's 12.5 over 12.5 plus 7.5, or 20 times minus 5, or let's just say minus 5 times that. Okay, so it's 12.5 divided by 20 times minus 5, or minus 3.35. 3.125. So the answer to 333 is this problem right here. This is my voltage, that's my current, or this is my V Thevenin, my R Thevenin, and this is the answer to 335. Okay, that's the end of chapter 3. Take care.